Okay, example 2. Determine the equation of the function graphed on the right with a minimum horizontal phase shift in the form y equals a sine of b times x minus c plus d. A is greater than 0. So more of the same, different looking graph. Let's start looking at this. So number 1, I'm going to calculate the amplitude because I can easily read the max and the min values. I have a max value of, yeah, be careful with this. This is 0.2, so right here, this is 0.6, so the maximum would be at 0.5. So that's 0.5. And then the minimum here, this is negative 2.6 right here. So this right in between, that would be at y equals negative 2.5. Okay, so 0.5 minus negative 2.5 divided by 2. So I get an a value of 1.5. Okay, so I'll put a box around that. Number 2. Let's think about, let's find our d value, our vertical shift. So we know the formula, maximum value equals d plus the absolute value of a. Okay, so what does that get us here? Maximum value is 0.5 equals d plus the absolute value of 1.5. And that's our a value from before. So that is 0.5 equals d plus 1.5, and therefore negative 1.0 equals d. So let's put a box around that. Number 3. I'm going to label 2 points. Okay, so I need to find the b value. So I'm going to look at this in terms of what is the period. Then I do my calculation to find the b value. So if I start with d equals negative 1. So where's our sinusoidal axis here? So here's negative 1. Okay, that's our sinusoidal axis. So if I start from, I'm going to do this, folks. I'm going to start from here. On our sinusoidal axis, I'm going to go from point A to point B. Why am I doing that? Because that's one full period right here. So one full period, okay? That's one cycle, one full period. So if I go from here, which is, that's 3.5 pi, and then I go here, right here. So this is negative 0.5 pi. What's the distance between those two? That's our period, folks. Okay, so period is 3.5 pi minus negative 0.5 pi. That's the distance. So I have a period of 4 pi. If I have a period of 4 pi, remember, period equals 2 pi over the absolute value of b. So I'm going to go 4 pi equals 2 pi over b. Let's solve that algebraically. That's 4 pi b equals 2 pi. That's b equals 2 pi over 4 pi, and that is b equals 1/2. Okay, put a box on that. Remember, the other way to look at it is in terms of sketch out, in this case, right, 4 pi, it's double the period of the standard sine function. So y equals sine of x has a period of 2 pi. This transform function has a period of 4 pi, right? So that should automatically tell you that the b value is 1/2, right? Or you can think of it this way. If I sketch this out, folks, like this, let's go 2 pi. So this would be exactly 2 pi. I've done exactly half a cycle, so that means b is 1/2. That's the other way to think about it, okay? So also think about it like this: half of a 2 pi, sorry, half of a cycle, therefore b equals 1/2. That's the other way to think about it, okay? Let's see. Let's think about our C value, horizontal phase shift. So number 4. And I'm going to just make some room here. Okay, number 4, folks. At point A, shift was pi over 2 radians to the left. Okay, so if you imagine the sine function like this, because remember the sine function always starts from the sinusoidal axis, I'm going pi over 2 units to the left that way, right? So that's our that's our horizontal phase shift. Okay, so let's write out the rest of that. At point A, shift was pi over 2 units to the left. Therefore, C equals negative pi over 2. Okay, let me put a box around that. Let's take stock of all our transformation values. A equals 1.5, D equals negative 1.0, B equals 1/2, C equals negative pi over 2. So what does our final equation look like? I have y equals a sine of b x minus c plus d. That transforms to y equals a value is 1.5 sine of b value is 1/2 x minus negative pi over 2, that's x plus pi over 2. And then my d value is minus 1. Okay, so there it is. And I will leave in your notes and on D2L, I will leave the same link to the Desmos, where you can play around with Desmos and see these transformations happening in real time. Oops. Okay. Part B. State the equation of the function in the form y equals cosine of b times x minus c plus d, where a is greater than 0. Use a minimum horizontal phase shift. So first of all, since we're talking about the equivalent cosine graph, these values are not going to change. We're not vertically stretching it anymore. We're not horizontally stretching it anymore. And we're not vertically shifting it. So all those values are the same. What is my C value? I need to make a phase shift to match this transformed graph and make it in terms of cosine. So what is this in terms of cosine? Okay. Let's label on here point K. So I'm going to label this right here. Let's call this point K. If I look at point K, let me clean this up a little bit, folks. Okay, if I label point K there, folks, okay, we know that the cosine function always starts at its maximum, right on the y-axis, right? So clearly we can see right here, what is that distance? What is that distance or that phase shift that had to occur? So it's a phase shift to the right, right? So let's write that up. Okay. At point K, graph of cosine function was shifted to the right by pi over 2 radians from its original start on the y-axis, right? We know that because that's how a cosine function works. Therefore, c equals pi over 2. Okay, so the a, b, and d values are all the same. What does the new cosine function look like? Well, it looks like this. So y equals, a value is still the same, cosine, the b value is still the same. Well, from the original cosine function, I'm shifting it to the right, so that's minus pi over 2, and then the d value of the vertical shift is still the same. So that's my equivalent cosine function for that. So those are the equivalent functions. They'll make the same graph. Okay, there you go. Okay, example 3. Another example. Determine the equation of the function below with a minimum horizontal phase shift in the form y equals a sine of b times x minus c plus d, and the form y equals a cosine of b x minus c plus d when a is less than 0. This a is when a is negative for both, okay? So let us begin here. So number 1, I'm going to calculate the amplitude. Okay? A equals max minus the min. So that's the max of 5. There's a min of -1. So 5 minus -1. So let me max minus min divided by 2. 5 minus -1 divided by 2. So my a value is 3. But since a is less than 0, a is equal to -3. Okay, so there's our first value. A is -3. Number 2. Let's find our d value. Maximum value equals d plus the absolute value of a. That's 5 equals the d value plus the absolute value of -3. And that's 5 equals d plus 3. That's 2 equals d. Okay, so there's our d value. Number 3, what's our b value? Well, let's look at it in terms of period. Okay, so I'm going to go from a to b. With a d value of 2, there's a sinusoidal axis. Y equals 2. I'm going to pick 2 points. I'm going to go a here. I'll note where that starts, pi over 6. And then I'm going to go full period. So this is point A. This is point B. Where does it end? Okay. My period is 5 pi over 6 minus pi over 6. And that equals 4 pi over 6. Or my period is 2 pi over 3. Okay? But I need a b value. So I know that period equals 2 pi over absolute value of b. So that means 2 pi over 3 equals 2 pi over absolute value of b. Therefore, b must equal 3. 4. Let's look at our horizontal phase shift, our C value. I'm going to label two things on the horizontal axis. So the sinusoidal axis. Let's label point C right here, and let's label point D right here. When I take the sine function, right? So if I have the sine function, it would have started this way and then max there and then go out like this, right? But then we took, okay, but then we said the A value is negative, so we reflected it, right? So what does the reflection look like? The reflection looks like this, okay? So then, if the reflection looks like this, then I need to know what is this phase shift from C to D to get to my new function. Well, that is looks like that's pi over 6. So if I'm going here, here, that's pi over 6 to the left. So from C to D, that is a horizontal phase shift of pi over 6 left. Therefore, C equals negative pi over 6. Okay? Y, so let's write our equation. Y equals A sine of B times x minus C plus D. Let's take stock of all our transform values. Okay, so what's my A, B, C, and D value? So let me just highlight those. A value, D value, B value, and C value. Okay, so Y equals A value negative 3 sine of B value 3 times x minus negative pi over 6, the C value, the horizontal phase shift, or plus pi over 6, and then plus D, plus 2. Okay. Questions also asking, so that's our equation in terms of sine. It's also asking, what's the cosine version of it? Let us do this. If I put a point D right here, okay, so I'm going to, let me clean this up a little bit, folks. Okay, I'm going to clean this up. Let me clean it up. Okay, I'm going to redraw the sinusoidal axis. Okay, and then I'm going to label point E right here. If I had drawn the cosine function, it would have looked like this, folks. It would have started up here, and then it would have done this. Let me just draw a couple key points. Oh, can I draw a proper? Oh man, let me do this better. Okay. Point E, right? If I apply a value that's negative, right? Remember, the D value staying the same, the B value staying the same. I need to see what I need to do with the C value once I apply a negative A value, which means it'll flip it to this. So it'll flip it to this. And actually, let's take a look. Isn't that convenient, huh? Do I even need a phase shift if I flip this? No, I don't, right? So for y equals a cosine of b times x minus c plus d. Oh, let me write that a little bit better. Okay. Hang on, folks. For y equals a cosine of b times x minus c plus d, no horizontal phase shift is needed when a is less than 0. Okay, and we showed that through all of this analysis. Okay, so my a value is still negative 3 cosine. My b value is positive 3. I don't need a horizontal phase shift, so that c value is 0 plus 2. So when I simplify this, that's my final answer. That's what I get. Okay, so right there. Oops. And again, I'll leave the Desmos link in your notes or in D2L. You can play around with it and see real time how these transformations happen. All right, folks, application time. The depth, D in meters, of the water in the harbor at New Westminster, BC, is approximated by the equation D is a function of time, depth as a function of time, equals 0.6 cosine of 2 pi over 13 t plus 3.7, where t is the time in hours after the first high tide. So when you look at the tide levels, so that's the level of the water, how high the water is above a certain reference point, this can be approximated through sinusoidal functions. And we can do various neat calculations with it. So state the period of the tide. Okay, when I look at my general transformation model here, y equals a cosine of b times x minus c plus d. State the period of the tide. Well, my b value right here is 2 pi over 13. The period equals 2 pi over the absolute value of b, and that equals 2 pi over the absolute value of 2 pi over 13, and that equals 2 pi times 13 over 2 pi, and so the period is 13 hours. Okay. Graph the function for 2 cycles starting at t equals 0 using technology. So radian mode, do not forget radian mode. Okay, and then I'll show you some appropriate window settings. When you graph trigonometric functions, sinusoidal functions, you have to tweak that window to make it work. First of all, you have to be in the correct mode, radian mode. Okay, what does this look like? So let me set up my axes here. Oh. Okay. 1, 2, 3. 1, 2, 3 units there. Okay, none of them in the negative direction because these are all positive water levels, like tides. Okay, so there's no negative depths. Okay, so when I graph this, I have a couple key points here, right there. Come on. Right there. Okay. Oops, no, not right there. Right there. Right there. Got a minimum there. Right there. Okay, and so on. So my graph looks something like this. Okay. I should do this. This is gonna confuse you, so I'm gonna erase this red line for now. Okay. I'll draw it in later. That's for a different part of the problem. Okay. So that's my sinusoidal graph. Okay. What's my window? So x window is 0, 26, and 1. Okay. And then the y window is starts at 2, 2, 3, 4, 5, 6, 7. So 2, maximum of 5. And then, oh, that's why. And then the scale is 0.5. So this would be 2, 3, 4, and then 5 up here. Okay. Yeah. Okay, roughly. All right, so that's my graph. Let me just clean this up a little bit here. Okay, that's what it's going to look like. Okay, and then my other axis here, this is going to be 26, and this is going to be 0. Okay, and then units of 1. All right, so this is y1 equals 0.6. This is what I punched into the calculator, cosine of 2 pi over 13. Remember, radian mode, t plus 3.7 plus 3.7. Okay, there's our graph. Let's answer a couple questions. If a boat requires a minimum of 3.5 meters of water to launch safely, for how many hours per cycle can the boat safely launch? Well, first of all, we need to find 3.5 is right here. So if I graph y equals 3.5, that's y2 equals 3.5. And let's look at these key intersection points here. Okay. y2 equals 3.5 intersects the function at, so you can do this through your calculator, 3.95 comma 3.5 and 9.04 comma 3.5. So this is the two intersection points. So this is 3.95, 3.5, and this is 9.04 comma 3.5. Okay, and I'm just going to look at one cycle. It says per cycle, right? So I'm going to look at this one cycle, folks. just this cycle. That's one cycle, max to max, okay? I can see that this part of the cycle is below the minimum required depth right here in green, right? So I want to calculate what that green is a no-go zone. Like it's too shallow for my boat to launch, right? So I'm going to say this, too shallow, okay, for the boat launch. So let's calculate that. So my two x values, which is the time values, right? We need to know how much time at 3.5 meters. So 9.04 hours minus 3.95 hours, that equals 5.09 hours when depth of the tide is less than 3.5 meters. So this is the danger point. You cannot launch the boat because it's too shallow. I don't have enough depth. Okay, so in a 13-hour cycle, 13 hours cycle, 13-hour cycle, that's my period, minus 5.09 hours, that gives me 7.91 hours when water is at least 3.5 meters deep and boat is safe to launch. Okay, and this is an actual tide calculation that is done to make sure that we are safely launching our boat. Okay, last part. What is the depth of the water at 7 hours? So trace x equals 7, y equals 3.11 meters. So at 7 hours, depth is 3.11 meters. Okay? If I graph out, so if I show this graph like this, right? So if I show it like this, and oops, let me do this. If I say this is y equals 3.11 meters, so y3, if I draw this, that's the line, right? What does my sinusoidal function look like? Something like this. Okay, if I do the intersect function, this is at 6 hours, this is at 7 hours, this is at 19 hours, this is at 20 hours. So you can do this on your graphing calculator. Okay, depth is 3.11 meters. Also at 6, 7, 19, and 20 hours. Okay, so it's asking at what other times is the water level at this depth? Well, these are the 4 times that the water level is at this depth. So in this case, it's a sinusoidal function. So depth is a cyclical value. Why? Because tidal depth, so tidal values vary in cycles. Well, this is because of the moon and gravity, right? So depth is a cyclical value because tidal values vary in cycles. So for 2 cycles, so what's shown here is 1 cycle, 2 cycles. So all of this is 2 cycles. Okay, so 2 cycles. For 2 cycles, there are exactly 4 times when the depth is equal. Okay, so it makes sense that I have 4 different times over 2 cycles that the depth is equal in this case, and that's what we calculated right there. Okay, all right.